Kenny Kirby, and this is Lab 5, Faraday's Law. For the description or purpose of this lab, we were intending to explore the interaction between a magnet and a conductive tube made of aluminum foil, and this lab aims to provide a hands-on understanding of Faraday's Law and its role in generating an electric current and magnetic field. Some concepts used in this lab were the Biot-Savart law, Faraday's law, Lenz's law, Newton's second and third laws, and the derivative of magnetic flux with respect to time. The results that came out of this lab were that the average time it took for the magnet to fall through the tube was 1.25 seconds, and the computed time that I got was 1.09 seconds. Some of the fundamental properties used throughout this lab were magnetic field, magnetic flux, current, and magnetic force on a loop or ring. But we can get more into these laws or fundamental properties later on. The experiment itself was dropping a magnet through an aluminum tube 5 times and collecting that data and finding the average time that it took the magnet to fall through, illustrated there. I had 5 trials, and the average time taken was 1.253 seconds. And off to the side here, we can see some measurements of the tube, the magnet, and the results from the trials compared to the computed time. Some checkpoint questions. Why are we able to use a Ferris tube, for example, a steel pipe? And that's because a Ferris tube would contain iron, which may become an induced dipole and generate a magnetic field, which would impact the falling magnet. And what happens to the magnet through this tube, and how does that compare to a magnet falling in free space without a tube? The magnet ends up falling slower through the aluminum tube than if it was dropped in free space. Here we have the glow script code, which intended to find the geometry of the tube and the properties and visualization of the magnet that we could get into our space. And then I created code to find a function to calculate the magnetic field of the bar magnet and a function to calculate the magnetic flux. And then going on, we calculated the magnetic force from the tube on the magnet, and then I calculated the current in each ring. Then computing the typical B field at each ring and using magnetic force from this and gravitational force, I found the net force on the magnet and finished up by updating the magnet's velocity and position. Here's the glow script code output. We have the bar magnet, as you can see, with the rings associated and the chart of velocity versus time of the speed of the magnet. And finally, the output, which was the estimated time within the tube that the magnet took. On to some discussion questions. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise? And how do we know? Using Lenz's law, red corresponds to counterclockwise and blue to clockwise, as this is a combination that slows the magnet down. What happens to the dynamics of the system when you flip the magnet around? It would still be slowed down, but the currents would flow in opposite directions. How does the total time in tube of your real-world system compare to that of your computational system, and how might the computational system be made more accurate? There was a slight difference, possibly due to the splitting of the rings of current in the tube, with more being more accurate. And air resistance encountered by the magnet could also have had some effects or differences between the computed model versus the real live model. And what does the shape of velocity versus time plot tell you about the forces acting on the bar magnet? The forces are imbalanced for about 0.2 seconds initially, with increasing and then decreasing speed, but then it evens out for about a second before becoming unbalanced and increasing in speed again. And lastly, some what if questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The slowing force would increase until it was as strong as the gravitational force, preventing the magnet from falling. And if holes or slots were cut into the tube, how would this affect the ring currents in the model? The braking forces would likely be decreased due to disruptions in the normal flow of current through the rings of the tube, which would cause the magnet to fall through faster. Thank you.